All right, so looking at what we're talking about today, we're still dealing with some of the exponential logarithmic functions. I want to make sure to close out the applications of those from our lecture standpoint, okay? So as far as the lectures were concerned, first we looked at uninhibited growth. Then we looked at something that kind of has a growth cap to it, or what we call a logistics model, okay? Today, we're also going to bring in the decay, right? What happens when it's not growth, but something that's decaying, right? Decreasing in value. So those are going to be some different perspectives that we have to be careful of. So this first one here, right? Which type of model are we looking at? Uninhibited growth or something that has a cap to it? All right. So remember, uninhibited growth is going to look like that. P equals P naught e to the KT, right? As far as the textbook is notation. So does this model look like that? No, right? So this is going to be the model where we're saying, hey, something's going to be kind of capping a max value here. Okay. Now keep in mind with exponential functions, when we think about horizontal asymptotes, we don't actually get to the value, but we're going to be looking at it from the limit perspective. Okay. So that's one of the reasons I definitely wanted to look at this again. And I like this problem because it goes into kind of making sure we understand what stuff represent. Okay. So for A sub 0 here, they want us to go find, sorry, for part A, they want us to find R of 0. Okay. So if I plug 0 into my function, are we okay with that being 4,000 over 2,000 or equal to 2? Does everyone know where I'm getting the 2,000 from? The main thing there is just remember anything to the 0 power is 1. So 1,999 plus 1 is where I'm getting 2,000 from. But what does that represent? All right. So this is our revenue. Initial revenue is, let's just call it the initial revenue, but at time equals 0. So year 0. Now, they didn't give us a particular year at this point to kind of say 1999 or 2010. They're just giving us the model to work with to make sure we describe. But one thing we do want to be comfortable with is initial value, right? This is our initial revenue. Is everyone comfortable with that? Now, what's going on with this next limit? When they want us to find for part B, the limit as t goes to infinity of this function. What are we trying to get to? Oops. Anytime we use infinity or negative infinity with our functions, what part of the function are we looking at? Are we looking at a specific point, the middle of the function, or the ends of the function? The ends of the function, right? So this is kind of one of those things that, hey, I'm looking at end behavior, but what side? To the right. Thank you. Does everyone follow me though with that? Why it's important to do the infinities here? This will be one of those limits that I feel we can put in. But thankfully, what you'll find, it's more about making sure you can interpret what's being said. Okay. So for this particular instance, the real question we have is what's going on with the limit as t goes to infinity of this e to the negative 0.5t. All right, the 4,000 is just going to be 4,000, right? The 1 is just going to be 1. The 1,999 is going to stay the same, right? Those are constant values or a constant multiple. So our real focus is mainly on this piece here. What's going on with that exponent that we have to be careful of? It's negative, right? So make sure you remember a negative exponent, a great way to write that is as a fraction. Okay. The reason that it's nice to do that, and you don't have to rewrite it all the time. Once you recognize that you can do that, you could just say, hey, negative exponent, here's the outcome. But this is helpful because, hey, that's going to go to infinity. Well, this is that situation we've looked at pretty frequently now that, hey, anytime the denominator of a fraction goes to infinity and that's a constant value in the numerator, this whole thing is then going to go to 0. I was saying anytime you're doing a limit to infinity, okay, and you have a constant value in the numerator and the denominator just approaches infinity itself, right? It gets so small that we cannot distinguish it between 0 and the actual value. So that's always going to go to 0. Now remember, this is a limit. This is not us plugging in 0. This is us saying the limit as that E value gets so big, it causes that 1999 right there to go to 0. Okay. So when I look at this particular limit here, what value does it go to? All right, goes to whatever that numerator is here, 4,000. Okay, makes you see this is just 1, right? So 1 plus the 0 here stays 1. So 4,000 over 1. Here we go. So what numbers should always be here first? Probably then 1, right? So understand when we get this model, we should see 1 plus this in the model the way it's set up. Now, what does that mean to us though? As you see here, they want us to call this the R max, but why would they call this the R max? That's going to be the cap, right? But why use the letter R and why use the word max? That's going to be the maximum revenue that this function, right, is showing that can be earned, right? Now, be careful here. What we're seeing here is that the maximum revenue expected from this Red Rocks Incorporated. Okay, so if whoever's looking at this business, Red Rocks Incorporated, the maximum revenue they can get is what? Not 4,000. Be careful there. What would that be? 4 billion, right? Now, keep in mind, how did I remember that piece? This is one of those things that we talked about last week. Always watch for statements like what we have here, right? In millions of dollars. I think last week we did thousands, right? Thousands of dollars. So be careful with how we interpret that. With that said, this Red Rocks Incorporated, okay? I'm not a business person, but that incorporated means that this is something that's gone to the public level, right? So a $4,000 revenue may not be something that's interesting to a public domain. Okay, so making sure we interpret that correctly. Are there any questions though with how I'm getting to those values? So based on the model, can they earn more than this revenue wise? That's the maximum, right? That's what they're saying is, hey, given the constraints that we're basing everything on, this is the most we're going to get, right? We looked at an advertisement perspective. Now, what else would need to be considered here, right? Hey, this is just the revenue function, right? If we want to see if the company is profitable, what other function would we need? If you want the profit function, you need the revenue function and the cost function, right? So make sure you understand that other perspectives would need to be further. Okay. Any questions or concerns before that last piece here? Are we good with the interpretation and what these things represent? All right, so the last piece here says find the value of t and use the nearest integer here. So we're going to the nearest year, since t represents year, for when r of t equals 99% of the max. Okay. Now make sure you see here, whenever we see something like this, the way that we kind of interpret that piece there would be like, hey, 99% of whatever we're working with, okay? So this would be where we want to go find the value that, hey, 4,000 times 0.99. So R of T equals 0.99 times that 4,000 we just found. This is going to be 3,960. Now, as far as solving this is concerned, this is going to be a little bit more tedious than some of the other equations that we worked with, just because our variable's buried in the exponent. Keep that in mind. But what you're seeing here is they want us to say, hey, 3,960 equals this equation that we've been given from our function. Okay. Now, there's different ways to solve this, but if we want to try the most direct path, what I recommend doing here is looking at this as, hey, that's just two fractions on both sides, right? They're both rational setups. Since it's one fraction on both sides, through multiplication, we can do stuff like cross multiplication. But one nice thing about this is I can bring this to this denominator and then this over here to that numerator, and I'm going to be okay as far as the values are concerned. What you're seeing is I'm doing multiplication and division in one step. I'm multiplying both sides by the denominator, and I'm dividing by that 3,960 at the same time. All right. By looking at this as a fraction, we can interchange the numerator and denominator of the opposite sides of the equal sign. You can do it separately if you need to. If you need to see it separately, just do both sides multiplied by that denominator. That'll get rid of the denominator here, but it'll keep it on the left side. And then afterwards, divide both sides by the 39,600 so that way we can get into this nicer form, okay? Once that's said, make sure you see here, hey, my next step is to get rid of the 1 by subtracting from both sides, okay? The nice thing about subtracting this 1 here, when we do this subtraction, we're really just subtracting by this value on the other side, okay? So make sure you see, hey, 1, I can just write as a number over itself. Why'd I pick this number? Right? Well, hey, I need a common denominator, right? Make sure you text that out. So just go over there and say, hey, what's 4,000 minus the 3,960? And this will give us 1,999 e to the negative 0.5 t equal to 40 over the 3,960.
Why didn't we do that?
Huh?
Why didn't we do it last? Just 4,000 minus.
Because we got this 1 over here, right? We're trying to get this by itself because we want that t.
Okay.
So I had to subtract this 1 from both sides. So this, what does this equal?
One.
It's 1, right? But remember, I rewrote it this way so that those have a common denominator, right? And then that means, hey, 4,000 minus this 3,960 gives me 40. Just remember, hey, I got to keep that common denominator, okay? Now, what I recommend here, let's clean this up a little bit. All right, 40 goes into 396. We know that because they both end in 0. And you can always do a quick check. Does 4 go into 96? All right, we know it's even, so we know 2 does. But if you go to your calculator real quick, you just do 396 divided by 4. And hey, look, it works nicely. So that we'll have this 1,999 e to the negative 0.5 t equal to 1 over 99. All right, then we have to deal with this piece here. like I said, it's not necessarily like hard calculations here, but it's kind of tedious. Okay, not every equation is going to look like this. This is a specific type of model, right? If we were just doing uninhibited growth, that we're going to look at in a second, decay, the model's a little bit more straightforward when having to solve for values. But I felt like this was a good one to make sure we walk through so that we're all comfortable with, yeah, it looks different, but we got this. We can handle it. Just take our time. Okay. Now, with that said, I'm going to move this piece here. Now, whatever you do this division, make sure you see, because we had a fraction 1 over this, that's why those got combined together, because we end up just multiplying to the denominator. But the one thing we do need to be comfortable with, if we're sitting in this situation here, e to an exponent equal to something, how do we get rid of the e when solving? What do we have to do to both sides? Yeah, make sure we go through both sides, and we're going to say, hey, let's do the natural log on both sides. So we're going to do the natural log of this and the natural log of that. The nice thing about that is over here, we're just going to get the exponent. So negative 0.5 t equal to the natural log of this. All right, and then, hey, we just need to multiply both sides by -2. And we could put that in our calculator. Okay. Now, one thing I would point out here, when you look at your natural log, if you remember the quick just focus of a natural log, if I do a quick sketch of the graph of a natural log looks something like this. Just the base function here, if we look at this point here, what in the world is this thing doing? When x is 1 for the natural log of x, right, the natural log of 1 equals 0. Okay, anything to the left of that is going to be very small x values, which would give us negatives. Anything to the right of that, the x values are getting bigger, right? And we're going to get a positive back. So the way this is sitting here, is that bigger than 1 or smaller than 1?
Bigger.
Well, it's 1 over it, right? So it's actually smaller than 1. So hey, this natural log is going to spit out a negative number right now. Well, what do we have here in the front? A -2. So hey, look at that. Everything's going to come out positive, which I definitely want a positive here, right? We're trying to find in what year are we going to get to 99% of that maximum value. With that said, what we should get is a pretty decent sized t value here, right? Just remember, they want us to round to the nearest whole value. Okay. Now, one thing I would point out here, just kind of a side note as you're dealing with this, if you don't like the fact that there's a fraction in there, you could also go to your calculator and put 2 times the natural log using your power rule, power property of logarithms, 197,901. Okay, you're allowed to do that because anything with a negative exponent is a reciprocal, right? So you put the negative as an exponent, reciprocate, bam, there you go. But that goes back to our properties of logarithms that we looked at the other day. If I can remember what slide I put them on, y'all. Everyone go with this before I go to the properties? So a couple weeks ago, this was something that we definitely said we need to be comfortable with, is our property of logarithms. Okay, as we deal with these different things, they could help us. Remember, one of the things that I showed us is even in doing some of our derivatives, we can break it down from a quotient rule or product rule using logarithms to make it a little bit nicer to deal with. Okay, it doesn't always help, but that sometimes can help you. Okay, remember I did this extreme problem just to show like we will never do this derivative, but hey, look, logarithms help us out quite a bit. Something that was pretty extreme, I fit into one slide. Okay, now I think I erased a couple of things to get it to fit, but remember, it would have probably taken 3 or 4 slides to do something like this, but a logarithm can help us. Now, where do we need it now? Make sure you see here with what we were solving, Dealing with stuff like this here, we definitely need to be comfortable with our inverse property of logarithms. Okay. This here is just you saying that, hey, this negative can go to an exponent here where that whole thing is now raised to -1, reciprocate, move forward. Those are ways to make stuff a little bit nicer for you. In the end, as long as you're comfortable with your calculator and you're careful, you're fine. Okay, so keep that in mind. Are there any questions I could clear up about this problem before we move forward? All right, so let's go look at one of these decay problems. Now I'm going to try to go a little bit quicker here because we've definitely looked at the growth ones, right? This is an example of, hey, we were looking at uninhibited growth before. Now we're going to decay. So as you write this problem down, what's going on with the given derivative that tells us this is decay? It's a negative, right? What we need to remember here is that whenever we look at this here, this dn dt equals to kn. Remember, n is our function. Because you took a derivative of it and you have the original function, we know that n is going to be equal to ce to the kt. That's the only function that when we take a derivative of it, we get the original function back with some changes because of the chain rule, okay? That means then when we look at this right away, we should notice that like, hey, k is equal to negative 0.096. This is a decrease of 9.6%, okay? Now, the good news is that was given to us here at the beginning. That was a rate of decay. The part that you have to make sure you connect it to, hey, if I see decay, I need to use negative with my exponent, with my percentage, sorry. So make sure you see that connection there. Now, as we've looked at before, connecting these two things is important, okay? What do we remember from last week, though, what the C value represents? That's going to be our initial value. So when it asks us to find a model that works well with this iodine 131, right? What we want to see here is that, hey, n of t, so this is for part A, n of t equals n sub 0 e to this negative 0.096 t. They didn't tell us what the initial amount is yet, right? So this model, hey, anytime I have an initial amount, now I know what to do with it. So let's say you're dealing with something that, like around here, you're going into business, right? Well, one of the big things around here is chemical plants, right? If you're working with particular chemical, you might want to make sure you understand how things work when it comes to the chemistry side of things. Well, here's a model that, hey, I may not need to know all the details about chemistry, but if I know the rate of decay and how much I'm going to start with, I can get something that helps me understand moving forward. Okay. So with that said, here's our model. Are there any concerns? What does the part B tell us to do then? It says that, hey, we're looking at this decay rate of 9.6% per day. So make sure we catch that. I should have said that before already, that when we see T here, it's T days. All right. Always make sure you check that because different elements have different rates of decay. Some are years, some are days, some are hours, all depending on what's going on with what you're working with, okay? The second part, though, says, suppose that 500 grams of this are present at time 0. How much will remain after 4 days? Okay, so what's the first thing we need to change about our function? Right, so we just been given the fact that in 0 then equals what? 500. Now, keep in mind when we're saying that, it's going to be measured in grams. Okay, so let's keep that in mind as we move forward too. So we'll say, hey, n of t equals 500 e to the negative 0.096 t. With that said, though, they wanted us to find out how much will remain after 4 days. So what should I plug into my function to do that? Are we allowed to do 4 here? Like, real question, is T represented in days right now? Yeah, right. So make sure, always double check that, because like I said, we could be talking about another problem that's in years. We might have to make some adjustments, right? So always double check that, hey, we're working in days. So we could definitely go to this next part and just say, hey, what's in a 4? Okay. One of those things that we talked about last week is being comfortable with our calculator. So watch your parentheses when you do this. Make sure you don't forget your negative sign. And I'm just going to round it to the nearest gram. So we'll say 341 grams. Some of you weren't here last week. So is everyone comfortable putting this in their calculator? I'm sorry, I shouldn't ask. Not everyone was here. Are there any concerns with the calculator plugging these in? I think one of the problems we did, and I really didn't post the video. Sorry. I'll try my best to do that when I get home. That's one of those things that's on my, make sure I try to get done this week, and that's getting the videos up. But for those, I think it was Friday we did this. The previous problem, that was something else we had to plug into. So we definitely want to be careful plugging into some of these log-based problems, okay, when it comes to log growth. With this part here, though, next thing says, after how many days will half of the 500 grams of iodine remain? Okay, do we need to go through and solve this? Because really what they're saying is go set this equation. So if we look at part C, 250 equals 500, e to the negative 0.096 t. Do I need to go through and do all that solving though? Does the exponential decay completely change the behavior of an exponential from what we looked at last week with the uninhibited growth? Now, guess what? You could solve this. Hopefully, you see here. You could definitely solve this, and it's going to give you the answer. We set it equal to 250, and we solve. Okay. Hopefully, what you'll see here is solving that's going to be a little bit nicer than what we just did here. You would have to divide both sides by 500, simplify, and then do the natural log. Okay. But remember here, right? We know that half of it will decay natural log of 2 all over k. Just make sure you understand this is not a doubling time, but this, I would do something like a t with a sub h just to remind myself this is going to be how long it takes for half of it to be left. So I wouldn't use the uppercase t because we use that for how long does it take to double. But I'll put t with h if you wanted to do t 0.0.5 just to say, hey, this is half of what's going to be left over. We know it's half again because when I go do with this, my k value, is negative. The nice thing about this is, hey, I have a way to deal with this. I just need to make sure to differentiate that when I use variables. What you'll find with your business class, I think some of you said Jordy took business classes, right? When you get to the business math side of things, you have to distinguish between when to use what variable as far as discussing what you're working with, okay? So be careful with that. Correct. All right. Now keep in mind, don't use the negative here, sorry. It is a negative rate. The negative tells us it's negative, it's decreasing. By me putting this here is just confirming that it's decreasing. Okay, so what are we looking at, right? We're looking at how long it gets to half of what it started with, right? Look at this here. What do you get when you divide both sides by 500? 250 over 500, right? So it's going to be 1/2. What you'll see here is when you do the natural log of both sides, okay, what you'll see is that'll give us negative natural log of 2. Just because that right here represents 2 to the negative 1. Which, if you're wondering why I said you don't need the negative here, is because we're supposed to be looking at a half, not 2, okay? So that's why this little quick statement helps us as well. But it goes back to the fact that, hey, we're looking at doubling or half of something. This is where the two is going to come from. Okay. Does that help with that? Now, make sure you see here what, again, make sure you see what I put here, that this big T I'm working with, you could put an H for half. I put a 0.5 to say, hey, this is us looking for the time it takes for half to remain. This is what we call the half-life of an element. Okay, so one thing, you may not be given a rate of decay, you might be given a half-life. Well, this will help you find the rate of decay if you know the half-life. Sorry, I'm gonna erase my stuff. Natural life 2. Are we getting to 7 though? That makes you, if you accidentally put the negative in, you're going to get a -7 something, right? Just remember, I don't want negative numbers right now. But the reason that that works is technically I should be using 1/2 up here. Okay. If you're going to use 2, the best way I would say is just use the absolute value of K. That would help clean it up. The book probably doesn't have this set up for decay, but guess what? We can use the same thing here. So if you want to solve it though, remember, divide both sides by 500, do the natural log of both sides, you'll get here as well. But hey, let's take some stuff we've worked on and help us out. Any questions or concerns I could help someone with on this problem? We okay then with me showing how decay and growth, yes, they're different, but they still are exponential working together in that sense? What you'll see here is just our graph now looks something like this instead, right? A horizontal reflection is what we would call it. All right, so sorry, I fit all that in one slide. The next one, though, with the last couple of minutes, we're looking at future value and present value, okay? Now, what you're seeing here is just kind of what happens as we start using different perspectives. So the other one was definitely, hey, it's over a given period of time, the amount you start with, it's going to decrease exponentially. That's why we say that's a decay model that's necessary. Here, it's all about perspective. Okay. So if you're wanting to buy a house, and in this case, the homeowner wants to get new siding for their house, right? You need to save up some money so that you have enough to make that purchase. But if you're being wise about it, you're putting your money not in a bank account and just hoping it sits there and nothing happens to it, but you're putting it in a place that it can be invested, right? A savings account has a small percent increase, right? Investment accounts, right? This would be a good situation where knowing your options and what's a safe option for you, your money, so that you don't have to put aside the whole $15,000. You can put aside a smaller amount, knowing that interest will help you be ready when you need it. Okay, so if someone buys a house, you did an inspection, say, hey, your siding's fine right now, but know that in 5 years you're going to need to replace it. Okay, what you're going to find here is we're still working with that exponential model. Okay, in this situation, K is going to be a positive value. We're putting into a savings account, so it's growing. But what is it that we want to find? Right? Make sure you see here what they're telling us is really what we're trying to find right now is not the future value, because we know we need $15,000. We're trying to find the initial value, or what they call the present value. Okay. So is everyone good if I fill it in as such? Put that over here. Now, hopefully what you'll see here is if you already know you need to find the present value, instead of having to go through all this work every time, you can just use this equation to help remind you. Divide both sides by e to the kt. we'll have P over e to the KT equal to that initial value. Well, using our negative exponents, guess what we just created? It's almost like an exponential decay model in a sense, right? I know what I need in the future, so I'm going to look at the model backwards and use decay rather than growth. But keep in mind, our starting of this is just using an account that has growth. And we're just trying to say, hey, given this interest, right? Given knowing that this is going to be the interest of growth I should expect, compounding continuously, what should I put in now? Okay. With that said, we can go through the solving every single time, or you could just remember, hey, I can use this where I use the value I need times e to the negative, the opposite of the percentage, right? I have a percent that's saying there's growth involved, so right now it should be the opposite of that. I can now solve this. Well, the good news is, sorry, they gave us T, huh? I didn't plug in T. I'm sorry, what should T be? My apologies. I should have plugged that in from the beginning. Well, I was about to say, the good news is, if you remember this formula, as they're trying to show you here, with a present value situation, you could just plug into your calculator. All right, so plug in our calculator and let's figure out what amount of money should be invested today so that 5 years from now we have enough.
Why is it in minus?
Is that, so remember, as I just said, what we're looking at here, let's look at the graph. We know that in 5 years, I want to be here. Okay, so what you're seeing here is this is going to be 5 years, 4 years, and so on. This will be year one. We want to be at $15,000. Okay, we know this is an exponential function. All right, what we're trying to figure out is, as I look at this exponential function, where's this value? No, it's not at 1. If you plug $1 into this account right now, it will not be 15,000 in 5 years. Okay, so that's why we have to be careful. We don't know what that value is. We're trying to find it though. Now, keep in mind, what were we given? We were given the interest rate there, that, hey, it's going to grow at a rate of 4.3%. Okay, we also know how much we need to have, which is the 15,000. Okay, so remember, as you deal with this, you could plug that straight in as such, and it's going to be positive. Okay, but what I showed you over here is, anytime you know that you need a present value, you could just divide both sides by the exponential part. Since we know the rate of growth and we know how long, that will give us this situation here. Now, keep in mind, when you bring in division with exponents, you're bringing in a negative exponent. The big difference is this is now P not equals, where it started as P. That's the big difference. I'm not looking for a future value. I'm looking for the initial or present value, as they're called. So that's the thing that you want to see here. Am I putting P or am I putting P not? P sub 0. Because of that, this exponent needs to be opposite of what it should be. That help? It's different, but just kind of make sure you're always kind of stepping back. Hey, what's my perspective? Right now, I don't know my initial value. I know I need $15,000 though to redo my siding on the house. I've worked with a contractor and he said, hey, based on everything, I could quote you confidently that even in 5 years, it's still going to be $15,000. Okay. Well, how much do I need to set aside now to make sure that I have that? Well, I'm going to use this perspective instead. Yes, I use the opposite exponent though, because now I'm tracing my exponential graph backwards. We're using a horizontal reflection to help look backwards. Does that help with that?
Yeah.
Okay. But then hopefully you see here, it's just making sure, hey, change my exponent and switch P and P not, the P sub 0, right? When I do that, what we find here is this value we're trying to find. I want to make sure that I initially set aside about $12,000, probably closer to $12,100, right? Now, this would be a situation, like say you're investing in an apartment complex, right? So you have the money that you need to deal with stuff and you're investing in this. And you have one of your friends come through and do your inspection for you, right? So that you know what you're getting yourself into. And they said, hey, one of the things I'd point out to you is that, hey, in about 5 years, you're going to need new siding. Based on the dimensions, everything, I can confidently say it's probably gonna be about $15,000 to do this. Okay, hopefully they're taking into consideration like things like the fact that the cost of supplies is going to grow over time. Hopefully they're considering those things. Those would be some things to take from this, right? When we talk about inflation, that hopefully that's a part of this problem, right? You're making this investment. What that means to you is that, hey, as I set aside my money for this project, buying an apartment complex, I am right now going to set aside $12,100. I know I have an investment account that's going to earn $4,300, and I'm going to have that money available to me in 5 years when I need it. With that said, if I put in this $12,098, sorry, $12,098.12 in 5 years' time, I know we'll have how much money growing at the 4.3%. $15,000. We can confidently say right now, if I invest $12,100, sorry, just to round it again, in 5 years, in this 4.3% compounded continuously, I will have $15,000 to pay for that siding. Okay. Any questions or concerns here? As we close out right here, one thing I would point out, I used a situation where, like I said, this could be very much a situation you run into, even when buying your own home, buying a car, right? If you're buying a used car, figure out when you're going to need new tires. If you know you have a decent investment account that you could still access the money, you could set aside the money to start with so that you have it ready for when you do need new tires, right? Those would be examples of personal stuff. I can do the same thing here though. Let's say you know you need this stuff 20 days from now for a project, right? The project might take a few days to do it. How much would you need to get at the beginning to make sure that you have enough for the whole time, right? There might be constraints where I can say, hey, let's do a present value for this situation, right? Even if you wanted to buy it today, knowing that, hey, I'm not going to need it for 5 days. How much should I buy today for when I need it? Okay, those would be different situations that you would want to consider, especially if it's like, hey, the only way to transport this is going to be by truck and it's going to take 3 days for that truck to get here. We can use that, just makes you see here, if you have a negative 9.6%, the present value is going to say, make it positive because we have to use the opposite sign. Okay, so those would be one thing I would point out here. Any questions or concerns as we finish up today?